This is problem 2419. In this problem, it describes the distribution of 7 charges. One is a big charge Q, and then it says that there are 6 little charges, little q, that are arranged such that each one is pointing towards the face of a cube that surrounds big Q. So big Q sits at the center of a cube, and the little q's point towards the each of the faces. So I can attempt to draw, and you should look in your book for a good drawing of it, but it looks something like this. And the main point is that this is at the center. Each one of these is pointing evenly towards the face. And the question is, what is the electric flux through one of the sides of the cube? So, if it's an electric flux question, it's a Gauss's law question. So we're looking for phi E, and we know that's the same as the integral of E dot dA. That's what the electric flux is. And this means we're integrating all the way around a surface, an enclosed surface. Gauss's law tells us that this flux, total flux of the surface, will be equal to the total charge divided by epsilon naught. So we can go ahead and do that part of the problem. The total charge is the big Q plus 6 times the little q. So Q plus 6 little q. So the right-hand side for the flux we can actually go ahead and calculate. We know all the numbers. But we didn't really ask for the total flux. This will be the flux over the entire surface. It asks for one face. So this is a case where you have to use symmetry. You have to use the fact that each one of these is evenly spaced and pointing to pointing to an individual side, and they're all equally spaced relative to a side. Okay. It doesn't quite explicitly say that in the problem, but when you look at the diagram in the book, you can tell. And what that means is the symmetry of that tells you that no matter which face you're looking from, the distribution will look the same. You'll always be, if you're looking from here, you'll see this one close, these 4 in a plane, and that one far. If you're looking down here, this one will be close, these 4 in a plane, that one will be far. So it'll always look the same. So if the charge distribution looks the same from every surface, that means every surface must get the same amount of that total flux. So the symmetry allows you to say then that the flux through one side is equal to 1/6 of this total, which we can start to figure out. That's 1/6 epsilon naught. And we know then the two values of Q. Big Q is 5 microcoulombs, and little q is minus 1 microcoulomb. So 5 times 6 times minus 1 is minus 1. So the total charge is minus 1 microcoulomb. So then the answer is minus 1 microcoulomb over 6 epsilon naught. So let's go ahead and just plug in and see what that is. If we're going to go to MKS units, that's minus 10 to the minus 6 coulombs. Minus 1 times 10 to the minus 6 coulombs over 6 times 8.85 times 10 to the minus 12 coulombs per Newton meter squared. And if you run the numbers on that, that is just minus 1.88 times 10 to the 4 Newton meter squared per coulomb, the unit of flux. Newton meter squared per coulomb. And that's the answer.